Hello everyone, this is Professor Ma and this is the sections Cavalieri principles on volume, basically volume. But we'll start with area. Okay, so let's go back to the ideas of the area is the sum of very thin strips. Okay, and I add thin strips together, and then the additions and then in turns change into integrals. And actually, the area of the each thin strips is in this case cross-sectional length times the width dx. In this case, in the pictures, they all straight, but in reality, this measurement doesn't have to be straight. I could have a shape that looks like that, and if I can keep track of the length of the being in each of the strips in here along the side, and then times the dx, that will be approximately area of each strips that are add strips together. So in other words, the approach doesn't have these straight lines. It could be wavy curves as long as I can trace the length of those curves. And we're going to apply somewhat to this principle to volumes. Okay. So we start out with the areas, the integral of the cross-sectional length. So the simplest case is for the two triangles. So if I have two triangles with the same base and with the same height, I put a sideways over here. And then if I draw a line cut across, the cross-sectional length, these two pieces U and V, they will be the same. Okay, and you can measure that. So in other words, this is they have the same area because the cross-sectional at each one of these cross-sectional, they are the same. The top one is equal to the bottom one. In other words, in this case, actually, if I have if I double this one, okay, I can cut this one and put this side on this side. I can stack the blue triangles into this rectangle right here. And in fact, both of them you can do that. That is, you can restack both these easily back into this rectangle right here. So that was the area. Okay. Like we said, the lines that we extract, they don't have a straight cross-sectional length. In this case, if I want to calculate the area of a circle, I can envision it like this. Suppose this is a circle of radius r, okay? And I think of them as in the following manners, that here from here to here is r, and so I take, if I view this particular map in as a very thin strips of circle, but that circle basically have delta x as the width. I straighten that out, and that's a circumference. It will be 2 pi r, and I do this and stack all those lines together, and that's then the total area. Okay, it's going to be 2 pi x. Follow the line. If I stack them together, the boundary line is going to be 2 pi x. And each one of these is the thin area is 2 pi x dx delta x. Okay, and then I add them together, right? And that turns into integral 2 pi x. 2 pi x dx, 0 to r. Okay, and so in other words, another way to look at it is the area of the circle is, if I straighten everybody out, it's going to be the area of this triangle. And you calculate the area of this triangle, you easily see this gives you the area of a circle pi r squared. Okay. So this is another kind of variations on the Cavalieri principle. Okay. Similarly, if we integrated the cross-sectional area times dx, and this is what we call dv, okay, and we have that sausage slices into slices. So one very basic principle we see all the time is we have a stack of paper, right? Stack straight. If I push the paper a little bit, then the paper is kind of lopsided. The volume those paper occupy don't change because each sheet occupy a specific volume, and so the stack doesn't, the volume doesn't change. Okay, this is the base. This is the Cavalieri's principle. Okay, and calculations confirms it. Okay, in particular, one shapes that is applied to is what we call in mathematics the prism. What's a prism? A prism is you take a base, a flat base, an area. Then you take the base, you move it across space. Okay, and then the space it cuts across, that forms a prism. If I take the base, I move it straight up and down. If I take this base, move it up and down straight, then we call this prism a right prism, a right angle straight up. Since the cross sections of each of these two shapes is they are the same, so they have the same volume. Okay, so prism with the same base, with the same height, have the same volume. Not only that, I can take this, I can twist it. I can have the shape goes up, but at the same time rotates itself. The same principle. Okay, they will occupy the same volumes as the one that's straight. So in this case, for instance, in this case, like the staircase over here is a bunch of the base shape is the steps. Okay, and the way it is made is is rotating through space, but every few inches of what, and there's another piece of wood. But what I'm saying here, suppose I filling every one out, I take the steps and filling all the steps, and so you think of it, all the steps are filling. After I fill in and think of them, they can rotate. Then what you wind up basically is that you wind up with the steps right here, and you can rotate them into the cylinder. Okay, and that's what all the wood stacks up together into solids. And so what's the volumes of these things? It's going to be the steps times the height. Okay, so that's the same thing as that. So because these cross sections area are the same. Okay, at each level, and the area cross section area is equal to the area of the steps. Okay. In nature, we have a lot of these twistings, and why not just straight occupy the same volume? Because the difference between these shapes and the the prism straight up, this one with a twist it has a lot more surface area. Okay, and then in biology, then sometimes you want to maximize the surface area to get to be able to transfer nutrients or release heat or something, balance heat or some other reasons. You want to maximize the surface area but occupy the same volume. Okay, so that's what's interesting of that shape. A cone is where you take the base shape and you shrink it to a zero. Instead of just move it straight up, you move it straight up. At the same time, you shrink it to a point. Okay, and then I can do an easy calculation. Suppose I put the x-axis pointing downward. Okay, and measure from top down, and say top is zero going down, and like a plumb. And put downward, and I say what's the radius r as a formula in x. Okay, because I want the cross-sectional area. I want to know what this cross-sectional area is to get a volume. Okay, and that in this case we use these similar triangles. Okay, these two triangles, and you can figure out R as a formula in X. And then you take these, and then the circular area is pi little r squared. Okay. So we get the circular area is that. Of course, r over here is a number. R is the original, how the base, the radius of the base. And then the area times dx, this times dx is this area times a slivers of dx over here. And this is what that is. And I'm adding them or integrate it from 0 down to h. And then I get the volume of the cone. In other words, if I don't have these, pi r squared h, that's just the volume of the cylinder. And if I shrink it to a point, only have a cone, that's a third of the entire cylinder. Okay, so that is true for all cylinder. All cones sits inside the cylinder. That the prism. Okay, it's one third of the prism, the corresponding prism. Okay. So all these is going to be 1/3 of the prism. These have the same volumes as long as the cross section is the same. So this is true for every cone. It's going to be 1/3 of whatever the prism. The prism is going to be the base times the height, right? And so take 1/3 of that volumes. The base area times the height it goes to. That's the cylinder. Then you take 1/3 of that. Here's another volume of sphere that justified through using Cavalieri theorems. Okay, and so we're going to calculate the volume of top half of the sphere. Okay, we're going to compare it to a cylinder. Okay, with the same radius. Okay, with the cone drilled out. So if I take a cross section AX and I take a cross section of the cone, remember the cone's out, but the band of BX, the claim is these two areas are the same. It doesn't matter where X is. If it slides across, the band is the same as the circle. Okay. This is a basic. I leave it up to read the math, and basically it's a very straightforward Pythagorean theorems. Okay, and but on the other hand, I know. So in other words, so the areas of these things around the volume of this surrounding with a cone drill out is the same volume as that. Half of a sphere, but the volume of this with a cone drill out, that's pretty easy. That's pi r squared times the height, which is r again. Okay, so pi r squared times height. Take away the cone drill out is 1/3 of that. Okay, 1/3, and this is pi r cubed, if you like. Okay. The cone is 1/3 of that. So what's left is 2/3 pi r cubed. And that's half of a sphere. So the entire is 1/4 of pi r cubed. Okay. That's basically the calculations. What else interesting that we can shape, we can use Cavalieri theorems to calculate volume. One of the type that's interesting is these intersections of pipes. And this is a version of 2 pipes. There's a version of 3 or 4 or 5 pipes, comes in, and the joining at the center is a core where they all meet. And this core, like for 2 pipe, looks like that. And so the question is, suppose each pipe is cross section is R, okay? What's the volume of that kind of a dome shape if I put it straight up? So I'm going to take that piece of joint right here, the pictures, from here to here, from here to here, from here to here, and behind. Okay, they meet back there. And, okay, then from here. Oops, this is inside. I can. Here it is. Okay, and the pipe. One pipe is over here, and the other pipe is over here, perpendicular. Okay, that's where the joint, the seam is, and that's the seam on the other side. Okay. So this is a half of that volume. And take a slice. I want to know the cross-sectional area. In terms of what? Well, I have to set up my x-axis. I have measures. Okay, I go over there and put my survey scales. That's 0 down. Okay, down x. I'm down to r. Okay, and so no, in this case, actually, we're going to do this. We're going to set x. Oh, by the way, the radius r. I should have drawn this out, and this is at x level. Okay, and the questions is what's the length s as a formula of arc, as a formula of x. Okay, that's just from the Pythagorean theorems right here. So instead of calculating that, I'm going to calculate half of s, then double the answers. And the Pythagorean theorem says, oh, half of the s is square root square minus x squared. And so s is twice that. Okay. So, and this is s also, because this is symmetric. The pipe, the intersection, the four sides, if I if I make a rotations of the pipe, intersections are rotated 90 degrees, you couldn't tell the volumes, it's the same shape. Okay, so therefore the cross-sectional area is the square of s squared, okay, because it's a square. And that's a cross-sectional area. And I want to integrate that from 0 up to what? R. Okay, that's where the x are. Because beyond that, there's no more cross sections. So integrate 0 to R, and then we get this particular formula. Okay. And I have double. And what other shapes? And here's then other things we can use Cavalieri theorems. Well, here's another way where we can make things, arbitrary things, given some formula, making volumes out of it, which you can track make a solid out of it, which we can track the volume here. Like for example, this. Here's a half a circle. So I make so imagine on the ground, I make half a circle, okay? And then I'm going to make a bunch of poles as columns, and I'm going to make a bunch of bars as to support that. I'm going to put the sheet of plastic over all those poles, and I think I'm going to make get together a bunch of palm leaves and make a thatch roof out of it to cover those poles. Okay, but the base of the building is half a circle. Okay. And here's what it reads: semicircular base. It's cross sections. So I'm describing this being perpendicular to the diameter. So here so I'm taking the cross section in this way. I'm slicing this one, then perpendicular to the diameter. So I'm taking these cross sections of these shapes. Okay, And what about these cross sections? They are isosceles triangles. In other words, in these shapes, I'm going. There's some solve here at each. If I take a cross section over here, let me call that as a X. Okay. And then look at what I slice through in terms of volumes. I mean, imagine there's a invisible volume sitting in front of me, and you take a knife, you slice through those, and you can see the boundary, of the part you slice through. It's this and that. It's a right triangle. And isosceles means these two are the same length. Okay. So in this type of problem, so therefore, if I were to slice through here, then of course, that because the cross section on the floor is longer, so it's a little higher. So therefore, and there's the cross sectional area that will slice through. Okay. And at this end, the other end, if I slice through here, then the cross-sectional area is a lot smaller. So in building this, you can think of making a pole smaller, then making a pole that's longer until the center is the longest pole, and the highest pole is equal to the cross-sectional length. And then on the other side, it goes back down again. Then I put a top over it. So when you finish, it looks like that. So the difficult part about this type of problem is the description of the shapes. You have to reconstruct. It's very hard to reconstruct. Just read somehow. You have to sit back and think about what is it describing, and try to draw to get that shape. In fact, a lot of modern architectures kind of utilize that principle. You see building twistings and this type of minimum constructions. Okay, and then here it goes to the a process of finding the cross-sectional area, which is a triangle. Okay, so I want to know this right triangle, how big it is, and that again, and we look at it from top down, and to find out what length of this is. Okay, this is the base. This circle is right around, like looking like that, and so basically I want to know what this length is, and there it is. Again, Pythagorean theorems. Once I know that, then I can obtain the area of that cross-sectional triangle, the area, and so that's with all these derivations here. Okay. That I integrate that cross-sectional area, and I get it volume. Okay. And notice if I were to switch, if I were to put all this pole on the other side and put this beam on this side, and so everything's go on the other side, I get the same volumes. Okay, this is like now it's like a stadium. Okay, but the cross-sectional area compared to the other one, the same cross-sectional area. So these two shapes, these two solids have the same volume. Okay, so that's Cavalieri theorems. And then finally, we use the Cavalieri principles kind of generalized to a higher dimensional volume. What do you mean by 4-dimensional volume, 5th dimension? Okay, and so we use these cross-sectional volumes to push it upward to quote-unquote higher dimensional volume. Okay, that's it. Bye-bye, and until next time, bye-bye.